Now it's time to turn things over to Raja, Dr. GuhaThakurta, and talk about RR Lyrae stars and beating hearts of our Milky Way. Raja, take it from here if you'd like to. Tell us all about what you're going to be doing with RR Lyrae stars and what we're going to get to see tonight.
Thank you. So it's a real pleasure and an honor to be on All Space Considered. This is my third time on the show, and the first two times were in person. This is my first time on virtually. So I'm going to talk about RR Lyrae, the beating hearts of our Milky Way. Our Milky Way has many hearts, and we have discovered 200 of these hearts in our Milky Way, but others have found even more. And I'm going to talk about them in just a few minutes. Just a quick word about myself. I teach astronomy, and I have the misfortune of being the department chair at the University of California, Santa Cruz, Department of Astronomy and Astrophysics. My solitary sentence in this role will be over in a year and a few months. But I'll say a little bit about the science internship program that I help run later on in this segment. All right, so I'm going to talk about RR Lyrae, how we use them to study the structure of the Milky Way, and how our study and others like it are challenging Immanuel Kant's idea that galaxies are island universes. So let's take a look at what RR Lyrae look like. So here is a beautiful image put together by the OGLE team, the OGLE group that was based in Poland. And they took a series of images of a section of a globular cluster called M3, Messier 3. And if you look closely at this image, I'm going to turn my laser pointer on and put it right next to one of these beating hearts, right to the left of my laser pointer. To the left of my laser pointer, you see one of these beating hearts. They are pulsing in brightness. It's a time lapse and it's looping. So actually, even if it didn't loop, the stars loop. That's the whole point of it, is they go up and down in brightness. There's one right next to my laser pointer there. There's another one up here next to my laser pointer again. They're all over, actually. There's one in the upper right, just above my laser pointer. And you'll notice a couple of things. You'll notice they go up and down in brightness. They're not all in sync. Some are going up while others are going down. But they all look roughly the same brightness. And I'll come back to that in a moment. They look slightly bluer than the rest of the stars in the globular cluster. Like the really bright stars look reddish orange. These stars look slightly bluish or bluish white. And they all look like their average brightness is about the same. Okay, so I'm going to turn my laser pointer off now. So what makes RR Lyrae useful to study galaxies or study the Milky Way, galactic studies? Two things. The first of those is they're easily identifiable. It's like looking out of your window in a busy cityscape. Say you're in a skyscraper in Manhattan and you look out of your window, there are all these lights all through the city. And it's hard to tell how far away each of these lights is. And it's hard to know what type of light is shining at you, except you notice that a few of them are pulsing with this very characteristic pattern, or this heartbeat pattern. And you notice that they're pulsing, and you notice that there are some of these pulsing stars right in your neighboring skyscraper that's across the street from you. You know the distance to that skyscraper, and you find that all of the ones in your neighboring skyscraper have exactly the same time average brightness. So not only do they have an easily identifiable so-called heartbeat of brightness variations with time, periodic, and that's what I mean by repeating. And they're also standard candles. That is, if you average their brightness over time, each RR Lyrae's average brightness is like the other. So their brightness variations look something like this. You see time running on the x-axis and brightness running on the y-axis. This is an example of a single RR Lyrae being observed in a single filter, going up and down in brightness. You can see the rise time is very sharp. The fall time is somewhat slower, sort of like an EKG, and that's why heart beats. And here are some of our own measurements. This is from Yuting Feng's work. And we've made measurements of the same star. Now, not the same star as the one on the left, but a given star in 4 different filters, UGIZ, so ultraviolet light, green light, far red, and the beginning of the infrared. So, and you can see that these stars, the pulse is more extreme in the ultraviolet than it is in, say, red light. That's another characteristic feature of these things. Now, If we look at something called a Hertzsprung-Russell diagram or a color magnitude diagram, you can see that the RR Lyrae land somewhere there. They are quite a bit to the left of the brightest stars in the globular cluster, but you can see that they form sort of a horizontal sequence. So it's luminosity on the y-axis, so how luminous the star is, and temperature on the x-axis, temperature increasing to the left. So you can see these are hotter than the brightest stars in the globular cluster, but they also all have the same time average brightness. This is what I mean by standard candles. Now, before I talk a little bit more about RR Lyrae in our own study, let's take a look at our Milky Way galaxy. Okay, so here's our Milky Way, and I'm going to show you a time-lapse movie of the Milky Way. This is a beautiful time-lapse taken by John Rockman. He just used a digital SLR. He set it up in a game park in Kenya, took a series of half-minute exposures and stitched them together into a time-lapse. What I'll do is I'll get rid of the label so you can see, you can focus your attention on the movie itself. So there we go. You can see the rotation of the Earth. The sky gets darker. You see some shooting stars, some lightning, clouds, and of course, this apparent sweeping of our Milky Way galaxy across our sky is a result of the fact that we're observing it from the Earth, a rotating Earth. So this is our grand home, our Milky Way, and there's been a lot of beautiful computer simulations that have been carried out by people who specialize in understanding how dark matter works in the universe. They use supercomputers to do these simulations. I'm going to show you one of these simulations called the Illustris simulation. And what you see in bluish white is a representation of the dark matter particles that make up a typical galaxy. And what you're seeing here, as time goes forward, you can see time in billions of years counting up since the Big Bang in the lower left of the frame. But as time counts up, the rotation is just so you can get a 3D sense of the structure of dark matter particles in space. The universe isn't rotating at anything like this rate, but we are changing our perspective so you can see the buildup of dark matter in the halo of a galaxy the size of our Milky Way. So this is you're seeing in simulation time, in computer time, highly sped up because billions of years are going by in a matter of seconds of our time. You can see that stars are exploding, and the greenish and the red and orange are no longer dark matter. Now we're talking about gas and stars that you're seeing in the different colors. The blue is the dark matter. The blue that you were seeing earlier is the dark matter. So galaxies are supposed to be exciting according to the people who build computer simulations. And so we want to go out and look for this kind of structure in our Milky Way galaxy. Now, of course, we are stuck inside our Milky Way galaxy, so we are sort of studying it from the inside. So we want to keep that in mind. So what I'm going to show you next is an artist's impression of what the Milky Way would look like if it were viewed from the outside. That is, if you could take us, if we had a long enough selfie stick, we could take a picture of the Milky Way. This is what it might look like. I'm going to stop the computer simulation. The Illustris simulation is just beautiful. So here's what our Milky Way might look like from the outside. It says artist's impression because we've never really taken photographs like this. You know, the selfie stick would need to be too long. And on this scale, the center of our Milky Way is at the center of this frame. But our sun, which is symbolized here by this symbol, not shown to scale, needless to say, is located about 25,000 light years from the center of our Milky Way galaxy. That's our sun and solar system. And by the way, if you try to put a picture of our solar system and our sun in this picture, on this scale, the entire solar system would be smaller than a single pixel. So that's why the sun is being shown as a symbol and not to scale. Okay. Now let's take this Milky Way galaxy and let's remove these labels and let's put the galaxy sort of on its edge and let's shrink it. And on this scale, what we have done, and I'll explain who we is in a moment, is we've found RR Lyrae that are located very far away from the center of our Milky Way. And how far, you ask? It's this far. On this scale, instead of 25,000 light years, which is the distance of the sun from the center of the Milky Way, this pizza slice that you see here, every dot is an RR Lyrae star that we found, and this is the discovery of some of the most distant known stars in the Milky Way. They are up to 1 million light years away. So roughly 40 times the distance of the sun and solar system from the center of the Milky Way. Now, this is the work of a PhD student at UC Santa Cruz who's actually currently calibrating the Keck telescope, getting ready for tonight's observation. His name is Yuting Feng. And also the work of a former UCSC PhD student. She's currently a postdoc in New York at the Flatiron Institute. This is Emily Cunningham. Emily finished her PhD in 2019. And Yuting and Emily and Eric, whose picture I don't have here, and I, the four of us, are working together. It's one graduate student, one postdoc, and two faculty are collaborating on this project on Keck tonight. Now, we found these very distant stars in the Milky Way, and I want to explain that this is not unique to the Milky Way. We are finding stars that are so far away that it's about halfway to our nearest galaxy, Andromeda. And Andromeda seems to have stars located that are about halfway of the distance from Andromeda to us. And so talking about Andromeda, this is a digital mosaic that my students and I made in the early 90s. My undergraduate students at Princeton and my grad student at Santa Cruz, Phil Choi and Andreas Berlind, you'll see their names at the bottom. They helped put together this digital mosaic of Andromeda. And I say this, there's 4 versions of it at different contrast levels. And each mosaic consists of 57 images in blue and infrared light. This was the first digital mosaic anyone had made of Andromeda. We're talking about 30 years ago. Now, I'm going to remove all but one of them. And we're going to shrink this in size so we can see far away from Andromeda's disk. So there we've shrunk it. And there is this beautiful survey called PANDAS, which is a survey run out of a group in Canada that looked at the density of stars around Andromeda, and the grayscale, the inverted grayscale, the dark on light, is a map of stars around Andromeda. Now our group, the SPLASH survey, went out and measured the density of stars as a function of distance from Andromeda's center using the Keck telescope, and that's what you see in this graph here. So on the x-axis is distance from Andromeda. I'll give you that distance in light years in just a moment. On the y-axis is the density of stars as we march further and further away. So Andromeda has stars going out to nearly 1 million light years from its center as well, not just the Milky Way. And this was the work of the initial work on the outer halo of Andromeda was the work of Carrie Gilbert. She was a PhD student at UC Santa Cruz at the time. And I'm currently working with Alice Deason, a former postdoc at UC Santa Cruz, who's a professor at Durham University, who is studying the very outskirts of the Andromeda galaxy, with Emily and me. Now, the person who got me started on this road is none other than your very Dr. David Reitzel, because David's PhD thesis was the first to get spectra of stars in the halo of Andromeda in numbers that no one had done before. And this, David, you and I started this work, I still remember, on October 2nd, 1996. I actually have the telescope proposal from that observing run. And October 2nd and October 3rd were the first 2 nights we had for this project. They were the 2nd and 3rd nights of operation of the Keck 2 telescope. And we were using, at that time, the LRIS spectrograph to do this work. I think it was the Keck 2 telescope that LRIS was on at the time. Yeah. So a nod to David for really getting me started on this road. So the picture that's starting to emerge is in galaxies like Andromeda, the Milky Way. The stars go out very, very far from the center of the galaxy, practically out to the neighboring galaxies. And this challenges a very important notion that was put forth 250 years ago by a philosopher named Immanuel Kant. He put this forward almost exactly 250 years ago, 1755. Kant was a philosopher, and his perspective of what was then called island universes, what we now call galaxies, was that there are these islands of light separated by vast amounts of empty space. Now, Kant's idea was absolutely brilliant. because it was really in the realm of philosophy rather than science at the time. And it couldn't be tested very easily because we didn't have powerful enough telescopes, and his ideas sort of died out and wasn't very popular in terms of being discussed by the community for nearly 150 years, until the early 1900s came along, and two scientists, Curtis and Shapley, had what is now a famous debate. This is now 100 years ago, 1920, a famous debate about the ultimate nature of our galaxy. So Curtis was of the opinion that these islands that we see are far away from us and are just like the Milky Way. And Shapley was of the opinion that those islands were inside our Milky Way. And so they had this debate, and as data collection improved and measurements improved, it turns out that Curtis was right, that these nebulae in the distance were about the size of the Milky Way. They were just very far away. That's why they looked small to us. And Shapley, who thought they were much closer inside our Milky Way, was mostly wrong. I say mostly because there are stars, there are galaxies close to us, like the Large and Small Magellanic Cloud, that are inside the halo of our own galaxy. So there are some galaxies that are smaller and inside our own galaxy's halo, but most of them are far away. And so for our studies of the Milky Way halo, we use the twin Keck telescopes on Mauna Kea, and we use the Lick telescope at Mount Hamilton in California, very close to where I live here in Northern California. So here are the telescopes in question. The two Keck telescopes on Mauna Kea shown on in the upper left, and the Lick telescope with its famous sodium laser shining out. This is the Shane 3-meter telescope. 3 meters is the diameter of the Shane telescope mirror. It's a single mirror in the Lick telescope. And as Dr. Reitzel mentioned, each of the Keck telescopes is segmented. Each of them has 36 segments. Each segment is the size of a human being. Each of the Keck telescope mirrors, with all the segments put together, is about 10 meters in diameter. So 10 meters for the for the telescope on the left. Sorry, I'm just going to go back. 10 meters the mirror diameter for the Keck telescopes, and 3 meters for the Lick telescope. Now, because of the pandemic, the telescopes were actually shut down in the summer of 2020 when the pandemic first really hit the U.S. and mainland of the U.S. and Hawaii, and then in sort of the late summer they started opening it up, but they said you can't come to the observatory. We're going to start something called pajama mode, where you don't have to get into your street clothes. You can be in your jammies, but you can still use the telescope from your computer. So we're going to do that tonight. I'm not going out to Hawaii. I'm sitting at home in Northern California. My graduate student is sitting at home in Santa Cruz, and we're going to use the Keck telescope. And tonight, what we're going to do is we're going to use the Keck 2 telescope, one of the two 10-meter telescopes pictured above, and the ESI spectrograph. We're going to take obtain spectra of individual RR Lyrae stars that are located up to about 500,000 light years away. Not the most distant ones, those are too faint for us to get spectra, but about halfway out to the most distant ones, we're going to get spectra. So we can measure their Doppler shift from the spectrum and measure how fast they're moving in response to the gravity, not just of the Milky Way, but one of these neighboring galaxies that we're in the process of cannibalizing, the Large Magellanic Cloud. So we're looking at the effect of the Large Magellanic Cloud on our own Milky Way, the gravitational effect. And because we're doing this through Zoom, Yuting and I are going to connect through Zoom, Eric's going to connect through Zoom, we decided we would open up our Zoom windows, virtual windows, to other people. And this is an initiative called Shadow the Scientist. We're going to invite this audience here to come watch us work. And we've invited a worldwide audience to come and do this. Now, in the next few minutes, and this is really the last thing I want to say here, in the next few minutes, I want to talk about how Shadow the Scientist fits in to a set of initiatives we're running out of UC Santa Cruz that we call CREST. C-R-E-S-T stands for Creating Equity in STEAM. We are working towards creating equity in STEAM. We don't hope to achieve that in one person's lifetime or through one organization's efforts. But what we try to do is the horizontal words in this crossword puzzle are what we're trying to achieve. We're trying to create equity in STEAM. STEAM stands for science, technology, engineering, arts, and math. And the way we're trying to create equity is by engaging young people in critical thinking in the context of open-ended research under the close mentorship of world experts. And I want to emphasize why I personally feel this is important. We're in the middle of a pandemic, as we all know. We might be in the late stages of a biological pandemic, but there's another kind of pandemic that's been raging through the world for a little bit longer than COVID-19, and that's an information pandemic. And we saw this in the politics of the world, in the politics of the US, a pandemic in which evidence-based information was not being given its due weight. The loudest voices were being heard, not necessarily those who are the most expert in a particular area. The notion of that there is something called expertise was really at risk. And I would say was at risk, it still is at risk. With COVID-19, you start by vaccinating the elderly because they're most at health risk. With the information pandemic, you start by vaccinating the youngest people because they're going to live with this for the longest. And these efforts that we're doing, creating equity and STEAM, engaging young people in critical thinking through Shadow the Scientist and other initiatives, is really the vaccination for the information, one of the many vaccinations for this information pandemic that we find ourselves in the grip of. So it's a step-by-step process. We first want to take young people, and have them dip their toes in the water of STEAM. And that's what Shadow the Scientist is. It's an hour of a young person's time to say, let's see if this activity feels right. Who are the people involved in this activity? It's like saying, before you plunge into the ocean, you want to dip your toe in the water and see if the water temperature feels right. And more importantly, if the people who are already in the water feel like the people you want to hang out with. Okay, so this is what Shadow the Scientist is. It's dipping one's toe, allowing people to dip their toes in the water, especially young people, young children, educators. Once you know that, once you've done that and you say, yeah, this is for me, I want to do some more, you want to learn the swim strokes. And we do this through something called Python and Research, Pure, a tutorial that my students and I started, where we teach some of the techniques that you need to use in science today. Python is a very important programming language in science today, but we teach this in the context of research. And one of my colleagues in biomolecular engineering, Gio Chavez, teaches the programming language R in the context of research in computational biology. The first one, PR, is set in the context of astronomy research. The second one, computational biology research. And this is learning the swim strokes. Then you want to take the deep dive, and we run a program at Santa Cruz, a summer-long program. Now we're talking about a young person committing 100 hours or a couple of 100 hours of their entire summer to this. My wonderful colleague at Arizona State University, Annette Lee, she and I collaborate on something called We Are Stardust, where we bring in, as Annette describes it, two-eyed seeing, where a child looks at the universe through a Western lens, through one eye, looks through an indigenous lens with the other eye, and combines those two, looks through both eyes for the benefit of all. So combines sort of three strands in a braid: the science story, the cultural story, and the personal story. And after you take a plunge like this, you can take part in something called the Global Sphere Network, which is a community of practice of people who engage young people in research. So it's sort of a pay it forward attitude. We have an alumni buddies program. We follow the trajectories of students who go through this. We engage teachers in the science internship program. That's what TCEP is. We have a peer-to-peer college and career network. That's what P2C2N is. And then we involve community college students in the science internship program. Now, that's all the slides I have. And so I would love to see if there's any time for questions.
Well, I have some questions, although we're going to back up off this slide. But Raja, I do have a couple of questions. So you were saying that Kant's view was that there were island universes, but the research that we've been doing, well, that we kicked off together and that's been happening, suggests that they're not quite all so separate, that there's connections between everything. So how far out do these connections go? Is this something that is universe-wide, or where would you draw the line to say that we're no longer influencing each other?
That's a great question, David. I think it is universe-wide. I don't think it's unique to the Milky Way and Andromeda galaxies. I do believe that these boundaries of galaxies are very interesting. What does it mean for one galaxy to have ended and another one to have started? And the way you measure this is by measuring the motion of stars. If there's a particular star that's in orbit around the Milky Way, it's fair to call that a member of the Milky Way, influenced primarily by the gravity of the Milky Way. If you find something that's orbiting Andromeda, it's fair to call it a member of Andromeda. It's when you find stars that have been orphaned from both or are really in this tug of war between the two that you've defined the boundary. So that's the holy grail of this work. We haven't reached that yet.
Interesting. So you also mentioned that we're cannibalizing galaxies. And what's the evidence for that? What can you tell our audience about what you found?
I'll talk about not just what we've found, but what other astronomers have found. We can clearly see galaxies that are being ripped apart by one galaxy being ripped apart by the gravity of the other. So there is the Sagittarius galaxy that's being ripped apart by the Milky Way. And the reason galaxies get ripped is because the near end gets pulled harder than the far end and they stretch out. And once that happens, it's sort of a runaway process. So the Large Magellanic Cloud is something that's being cannibalized by the Milky Way, the Small Magellanic Cloud as well. Those are three examples of galaxies, one that is in the process of being digested, the Sagittarius one, but the other two are they're just coming into our, the Milky Way's alimentary canal, so to speak.
Okay, very, very interesting. One of our audience members in the YouTube chat wanted to know if any stars could be transferred from one galaxy to another, say from Andromeda to the Milky Way.
Absolutely. Not only can stars be transferred from one galaxy to another, what happens more commonly is when galaxies collide, their identities get lost as separate galaxies, and stars that used to orbit galaxy A, one set of stars used to orbit galaxy A, another set of stars used to orbit galaxy B. When the two galaxies come together, both sets of stars start orbiting a common center, and that's exactly what happens when galaxies collide. So the Large Magellanic Cloud is affecting the trajectories and motion of some of the stars that are, you could call them Milky Way stars, but they're actually being affected by the Large Magellanic Cloud as well. That's exactly what we're trying to study tonight, actually.
Okay, fascinating. Another quick question, and I'll see if Chris or Patrick has any questions. Why did you make Curtis Darth Vader in your Curtis Shapley poster?
I didn't. Whoever put that poster together did. And Darth Vader was correct in this case. Curtis was right.
Well, eventually he was correct. He did turn. And anyway, we don't need to get to no spoilers of Star Wars in this.
Right. The interesting thing is they were both correct in that debate, right? So is Shapley right when he says some galaxies are inside the Milky Way? Absolutely, but not all galaxies. Curtis, I think, was more right than Shapley. Most galaxies are outside the influence of the Milky Way, and only a few are inside.
One of our audience members wants to know, are RR Lyrae stars uniquely likely to be found in the outer regions of galaxies? So are they only found out there, or would you find them in the disk as well?
That's a great question. We are, from what we understand of, collectively as an astronomy community, what people understand of RR Lyrae stars is they have to be relatively chemically anemic. They have to be stars that are comparable in mass to the sun, but much more chemically anemic than the sun. Let's say roughly 30 times more anemic. What I mean by anemic, I mean the iron to hydrogen ratio in the sun, whatever that number is, in these stars, in RR Lyrae stars, that ratio is 30 times lower. The ratio of iron to hydrogen is roughly a factor of 30 lower. So stars have to be chemically anemic, and chemically anemic stars are actually very common in the Milky Way. They're more common than sun-like stars. The sun is unusually metal rich or iron rich. That's one condition. The second is the star has to evolve off the main sequence. Right now the sun is on the main sequence. It's converting hydrogen to helium in its core. It has to finish up using all the hydrogen in its core, become a red giant, and then it has to ignite helium in its core for it to become something called a horizontal branch star. And an RR Lyrae is a specific subclass of horizontal branch stars, where the chemical abundance is just right, not too low, not too high.
Gotcha. So by the way, for folks that are confused of how you could end up with anemic stars, remember the universe started out mostly hydrogen, some helium, little bit of lithium, and it was the stars that forged the heavier elements in supernovae explosions. Also collisions of stars as well. White dwarfs colliding will make a supernova explosion as well. But it takes those events to create the heavy elements. And in fact, it's the white dwarfs colliding that make a little bit more of the iron. So that iron tends to lag a little bit some of the other elements. So it's a very complicated story, but in general, stars that are made in a galaxy later in that galaxy's life will have more iron in them. So that our own sun was several generations down into the Milky Way's creation of stars. We were not one of the first stars formed in the Milky Way. Let's see here. We have got another question from our audience. And then Chris, if you have any, or Patrick, certainly join in. But somebody wants to know that when the Milky Way and Andromeda collide, will our sun or any other stars be flung outside the galaxies?
Absolutely. Stars will be flung outside our galaxies. It's hard to predict exactly which stars, but stars in the outskirts of these galaxies are more likely to be lost. Stars that are already tenuous in terms of their gravitational attraction to each galaxy, to Andromeda or Milky Way, those are most likely to be lost. It's unlikely for the sun to get orphaned like this. Galaxy collisions are like corporate mergers, so some people get laid off, and that makes the remaining organization even stronger. That's what happens. And literally, the stars that get orphaned carry away energy, allowing the rest of the system to settle into one galaxy. So they actually, the energy they take away is really important for the collision and merger process.
How about planets? Will they be safe if we could live long enough to see this happen on Earth? If
absolutely, yeah,
kill us in the process, let's assume. Would Earth be in any danger?
Not really, because the connection between stars and planets is the gravitational force is way stronger than the forces that stars experience during galactic collisions. So it's very unlikely for a star to come close enough to disrupt the solar system. Not in the Andromeda collision. There'll be other things that'll kill us long before that. Politicians most likely, but the sun bloating up into a red giant is going to be the thing that will fry the Earth, not the Andromeda collision.
Yeah, indeed. Chris, you're Patrick. Do you have anything you'd like to know?
I have a question.
Yeah.
Oh, go ahead, Chris.
Yeah, this is really fascinating. I mean, as someone who's interested in astronomy, I've always thought, sure, there are some stars out there between galaxies. Some will get ejected. Sure, I know that. But when you showed that chord looking out, that angle looking out from us, the number of RR Lyrae stars you found knocked me back. And the reason for that is I know RR Lyrae stars are relatively bright, much brighter than our sun. My question is, what else is out there as far as the population? Does it look like the population of our galaxy? Meaning, the yellow dwarfs, the red dwarfs. There could be a huge number of dimmer stars out there in this population, and you're just looking at the brightest ones you can see from here. Do I have that right?
You have that right, Chris. The RR Lyrae are not the absolute brightest stars that are out there. Alice is leading a project to look for very distant red giants. Those are the problem with red giants is there's a superposition problem. You have foreground red dwarfs that can masquerade as distant giants. So, but we're using the Lick telescope to look for distant giants that would be the comparable distance to these RR Lyrae, but even more luminous than for sun-like stars at these distances would be very difficult to find because they're so faint. I mean, this is already challenging to find RR Lyrae.
Yeah, I'm amazed. This is really something.
Now, I was wondering, Roger, what is the nature of the pulsation? What is the mechanism associated with it, and what is the period of the pulsation of RR Lyrae stars? Are they they have a regular period?
They do, Patrick. So RR Lyrae come in two flavors. The one flavor is called RRAB, and that's one flavor. The other kind is called RRC. The RRAB stars have time periods between half a day and 3/4 of a day, so 12 to 18 hours. There's some range. Some are even more than that. But most of them are in that period range. RRCs have shorter periods. They're between 1/4 of a day, 6 hours, to maybe 10 hours. 6. So, and they do have a range of periods. But your first question was, what causes this? And a star in a way, is a static nuclear bomb. The nuclear fusion that's trying to push everything outwards, the tremendous energy of nuclear fusion that's causing the star to shine is also trying to push everything outward. Radiation pressure driving the star outward is balancing its gravity. It's just balancing its gravity. And what happens in certain phases of stellar evolution is stars hit what is called an instability strip, where while these two things are balanced, they reach a dynamic of balance instead of a static balance. They oscillate about, it's like having a pendulum is a beautiful balance between the Earth's gravity and the tension of the wire that's holding the ball. It could be in static equilibrium if the pendulum is not swinging, but it could also be in dynamic equilibrium if the pendulum is swinging. So stars go through the swinging of the pendulum phase, which is this oscillation where the nuclear fusion, when it's winning, the star expands, and then gravity reins that in, it starts to compress. And so it goes through this very, very strictly periodic cycle.
Very, very interesting. Well, once again, thank you so much for joining us tonight, Raja. It's been a real pleasure hearing about what you're doing with RR Lyrae stars, about how more evidence that Andromeda and the Milky Way are actually probably joined by a bridge of stars. And you keep pushing this boundary out from the Milky Way and then out from Andromeda. And someday we'll hear that the two have, joined in the middle. Kind of like the Transcontinental Railroad. This is the transgalactic star trails, I guess, that are joining between these. And it's just fascinating to know that galaxies are no longer these separate islands, that they really do influence one another, and the universe is connected by these webs of dark matter that just really, we've learned so much in the past decades that it's just fascinating to hear all this work. So thank you again for joining us. And folks, like we've been saying, when All Space Considered ends tonight at 9 p.m., we will get a chance to join Raja on his Keck run, Keck 2, with the ESI spectrograph, where he's actually getting spectra of these RR Lyrae, and you'll get to see what it's like to be on an observing run. Now, you don't need to go anywhere. You could just stay right here on YouTube and watch our stream. We're going to stream it right along with the end of our program. So stay tuned for that, and certainly enjoy the program. And Raja, we'll see you in about 45 minutes or so.
Thank you so much for having me, David, and thank you for getting me started on this bridge of dreams to Andromeda. Thank you.